In this video, we will practice solving related rates problems. Problem number 5. A trough is 12 feet long and 3 feet across at the top. Its ends are isosceles triangles with altitudes of 3 feet. For part A only, suppose water is being pumped into the trough at a constant rate of 2 cubic feet per minute. How fast is the water level rising when the depth h is 1 foot? Include units of measure. I always like to start by writing down a list of all of the facts that we are given in the problem. Other than the dimensions of the trough, we are told that the water is being pumped in at a constant rate of 2 cubic feet per minute. So water is being pumped into the trough at a constant rate of 2 cubic feet per minute. So we're talking about an amount of water that's being put in the trough. So this is going to be a volume. And they're telling us the rate of change of this volume. So they are giving us dV dt. All right, the rate of change of the volume is 2 cubic feet per minute. And I'm going to leave it as a positive 2 because it's being pumped into the trough. If it was leaking or draining out, I would have made it negative. So cubic feet per minute. So that is one fact we are given. How fast is the water level rising when the depth h is 1 foot? And you can see that h is the water level. So that's another fact we are given, that in part A here, the depth h is 1 foot. And they want us to find this. How fast is the water level rising? So I'm going to write down both of those things. So we are to find, okay, the speed at which the water level is rising is the rate of change of this h. So they are asking us to find dH dt when h is equal to 1 foot. So this is what we are given. Now we need some sort of relationship that connects these things together. We need some sort of relationship between h and volume. So, well, right there, we're given volume. So we probably are going to need to work with the formula for volume. This trough is in the shape of a prism, and the formula for the volume of a prism is area of the base times the height. So be careful, when we talk about the height of a prism, we're not talking about how tall it is off the ground. We're not talking about the 3 feet. The height of a prism is the distance between the bases. So if we were talking about the entire trough, this red triangle is a base and the other red triangle is also a base. So you can see that the distance between the bases is 12 feet. So that would be the height of this prism. Now we have to be a little bit more careful because we're not actually talking about the volume of the entire prism. We're talking about the water in the prism. So the shape of the water is still a prism, but the base is smaller. So this tiny triangle is a base, and this tiny triangle over here is the other base. But guess what? The distance between these bases is still the 12 that we mentioned before. So that is still the height of this watery prism. So as I begin to build my formula for the volume of this water prism, I will come back to the area of the base, but we already know that the height is 12. Now let's talk a little bit about the area of the base. all right, the area of this small red triangle. I've drawn it a little bit bigger so we can work on it more easily. It's a triangle, so the area of a triangle we know is going to be 1/2 base times height. In this case, we mean the base of the triangle itself. The height of the triangle, they gave us a variable for it to use. All right, the height of this triangle is h. So the area of this triangle is 1/2 base times height. So I can go ahead and put the h right here. But what about the base of this triangle? We don't have a variable for that. So temporarily, I'm going to call this x. So that would make this 1/2 x times h would be an expression for the area of this triangle, the area of the base of this watery prism. But this is one too many variables. If I can avoid introducing a new variable x, I want to do that. So we can avoid having a new variable by using similar triangles. I've drawn this small triangle, which is the base of the watery prism. But what about this larger triangle, which is the base of the entire trough? All right, focus your eyes on this for a second. I'm going to draw a larger version of this now. For the larger triangle, we can see that the altitude, the height of the purple triangle, is 3 feet. So this is the 3 feet right here. Also, we know what the distance across the top of this triangle is. Looking back at the trough, that would be this distance right here, which is also 3 feet. So these are going to be similar triangles, so we can set up a proportion to find a relationship between h and x. Honestly, you should be able to tell, actually, just sort of by common sense, if the height is 3 and then the width is 3, obviously the height and the width are the same. So that tells you right there that the same should be true for the smaller triangle. The height and the width should be equal, so we kind of, by common sense, know that h will equal x. In general, it won't be that obvious, so I'm going to sort of go through the process, go through the motions of setting up a proportion. So in geometry class, you learned to do things like this. You would write a proportion for your similar triangles, saying things like small over big equals small over big. So if you look at the vertical, the height, the altitude, small over big would be h over 3. So that's 1 small over big. Now we're going to switch and look at this horizontal length. And we're going to make another fraction in the form small over big. So that's going to be x over 3. So small over big equals small over big. So h over 3 is equal to x over 3. And we can use this to find the relationship between x and h. But like I said before, this one is trivial, because if I multiply both sides of the equation by 3, then both of the 3's cancel out, and we just find that h is equal to x. So remember a moment ago I was saying, man, we really do not want to introduce a new variable if we don't have to. So you can see that we don't have to. Because x is equal to h, I can use this to substitute for x. So instead of x, I can just go ahead and put h because they are equal. So now we have this. So our formula for volume is coming along quite nicely. Let's simplify this. So volume is equal to, and remember we're talking about the volume of the water. So the volume is equal to 1/2 times 12 is 6, so we might as well go ahead and simplify that. And then h times h is h squared. So this is the formula that we can use for volume. Now we need to find rates like dH dt, and we're given a rate dV dt. So to get these expressions, we need to do some implicit differentiation and take the derivative of both sides of this equation. So if I do that, I'm going to have dV dt. All right, I've taken the derivative of the left side. And now I'm going to take the derivative over here. I have to use the chain rule because I'm differentiating with respect to t, and this is an h. So when the variables don't match, you have to use the chain rule. So the derivative of the outer function, I'm doing the power rule, so 2 times 6 is 12. So I have 12h, but now I have to multiply by the derivative of the inner function. And that's just going to be dH dt. Now, remember the facts that we wrote down at the beginning of this problem. We know that dV dt is 2 cubic feet per minute. So on my next step, I'm going to substitute 2 for dV dt. And we are finding dH dt when h is equal to 1. So I can also substitute 1 for h. So let's do both of those things. So this is going to become 2 is equal to 12 times 1 dH dt. All right, and we are solving this for dH dt. So dividing both sides by 12, that's going to give us that dH dt is equal to 2 over 12. Maybe I'll just go ahead and show this step. So 2 over 12, which of course is equal to 1 over 6. And we must include our units. We're talking about height divided by a time. So just looking back at our units, height was given in feet and time was given in minutes. So this will be 1/6 feet per minute. Part B is very similar to Part A, so I encourage you to pause the video and try to do this problem by yourself. Then hit play and see how you did. For Part B only, suppose that the water is rising at a rate of 3/8 inch per minute when h is equal to 2. Find the rate at which the water is being pumped into the trough. Include units of measure. Let's make that list of facts that we are given. The water is rising at a rate of 3/8 inches per minute. So we're talking about the water level, the height. They gave us the variable h for this. And we're talking about the rate of change of this height. So in other words, we are given that dH dt, the rate of change of the height, is equal to 3/8 inches per minute. When h is equal to 2. So that's really two facts that we are given. And then there's something that we are supposed to find. Actually, let me highlight this as well. So we are supposed to find the rate at which the water is being pumped into the trough. So the water going into the trough is the volume. So we are being asked to find the rate of change of the volume. So dV dt. From Part A, we already know the relationship between the volume and the height, so we can just use that again. So the volume is equal to 6h squared. So let's go ahead and take the derivative of both sides. So we can get dH dt and dV dt to appear. So that would be dV dt all right, the derivative of the left side. Now the derivative of the right side, using the power rule, I'm going to have 12h. But since we are differentiating with respect to time, and this is h, we need to use the chain rule and multiply by the derivative of the inner function, which is dh dt. So now we have this. However, we know some facts that we can substitute. We are trying to find dv dt. That's our question mark, so we're just going to leave that alone. But we do know that h is 2 in this scenario. So we're going to go ahead and substitute 2 for h. And we are also given that dh dt is 3/8 inches per minute. So we can put 3/8 right here. So if we do that, we have dv dt is equal to 12 times 2 times 3/8. So actually, if we slap some units on here, this will be an acceptable answer. However, I'm noticing there's a typo in the directions that can easily be fixed. The rate of change of the water height was given in inches per minute. However, in part A, everything, including the height, was given in feet or feet per minute. So it's supposed to be feet and not inches. So let's just cross out inches per minute and put feet, which I'm sure is what was intended. So how about those units? We are doing change in volume over change in time. Since the units of length are in feet, the volume will be cubic feet. And the units of time are minutes, so cubic feet per minute. Now, you don't have to simplify if it is a free response question, but if this were a multiple choice question, you would find 9 cubic feet per minute among the answer choices.